This is the beginning of the recording for Monday, May 4th, 7:45 a.m. section. Got about 100 seconds to go. "45." Another volume check here. That's not good. Oh, no, that's all right. Okay. All right. Good morning. Let's move that there. And we will have announcements at the end of class/end of recording. Each the warm up today kind of leads into the next thing. So let's just dig into this. We've got the definite integral from 0 to 3 from x equals, just to specify, right? So from x equals 0 to x equals 3, integral of the function 2 to the x dx. Now, if you're to graph this function, while you can interpret what this means as area, it technically means area. We just won't compute this by using some area formulas because, well, we won't have straight lines. You know, this 2 to the x is an exponential curve. It's a curve, it's not straight, so we'll have to do something else, something different, right? So let me do that. Okay, so what we'll do is practice and review the technique we saw last Wednesday, which is to first look at the indefinite integral. So you'll see what happened here. Up here's the definite integral. There's the question related to this, but a different thing is the integral without these x values of 0 and 3. So without that, to the x dx. Then this thing, unlike over here where this is a number, this is an antiderivative problem. So we have here 2 to the x over ln of 2 plus c, using one of the standard antiderivative rules from before we talked about substitution. Then based on, here's every antiderivative, and by every I mean when you plug in a different number for c, you're technically talking about a different antiderivative of 2 to the x. Then you pick an antiderivative that you want. The easiest one to pick is when you just lob off the c. Now in this line we want the plus c, but now going back to this question here, and I tried to align the text directly underneath so we can see. Now the definite integral from 0 to 3 of 2 to the x dx is, well, to practice that notation. Now, many of you will choose not to use it at all, and that's actually fine, but I just want to illustrate. You can take this, and there's a certain convenience of putting that down there. So 2 to the x over ln of 2 with this vertical bar, 3, 0. So the 3 is located at the top because this 3 was over here at the top, 0 is down here because of the 0 down there. The key thing to do, please careful here, is to make sure now to plug in 3 for the x first. You always plug in this upper number first, and then plug in this lower number 0 next. Okay, so this ends up turning into 2 to the third, right, plugging in x equals 3 first. So we wrote a copy of this over here, plugging in x equals 3 first, and then wrote a copy of this 2 to the x over ln of 2 again, now plugging in x equals 0 next. As far as final answers go, I'd be fine with this being left like that, but I just wanted to, since the opportunity presented itself to talk about it, I just would like to mention Well, there's 8. 2 to the 0th is 1. Since you have the same denominator, a common denominator of ln of 2, you have 8 over ln of 2 minus 1 over ln of 2. You can simplify that to a 7 over ln of 2. Okay, so again, the definite integral that we started with in the warm-up, we first took a moment off to the side, looked at the indefinite integral, and now that we had this part of the indefinite integral, just leaving off, so leave the plus c here in this, but then leaving off the plus c when looking at going back to the definite integral. These problems are related, they're just not the same. And I say this because a very common error people make is to set equal the definite integral and the indefinite integral. So here are 3 examples of these. These are all, to me, I mean, they look a little different, sure, but they're all examples of setting the definite integral equal to the indefinite integral. So first, here's the original question. None of these 3 here would be correct to write. So here's taking the definite integral and literally setting it equal to the indefinite integral. Now, I get that there's the definite integral, and the next step is the indefinite integral, but just write the indefinite integral on its own line. This version of the error is, well, taking that same definite integral, and you'll notice this was the result of this indefinite integral, right? So right here, this was the result of the indefinite integral. So it's really the same error right here and right there. And then this one's sort of just in reverse. So here's the indefinite integral. And then this is the result over here, at least one of the results of the definite integral. So all of these are examples of setting an indefinite and a definite integral equal. This one's much more literal about setting equal an indefinite and a definite integral, so don't do that. These other versions are taking like a definite integral and the result of an indefinite integral, or an indefinite integral and the result of a definite integral. So please don't set those equal. There's a lot of moving parts I get, but in the process of doing this, you have a definite integral off to the side. Momentarily, we're looking at an indefinite integral. So you complete this antiderivative problem, and then you use this portion of information right down here to complete the definite integral problem. So there's a bit of back and forth to be careful of. And an equal sign, I think sometimes people use to just mean the next step. But there are times equal signs should appear, and there are times equal signs should not appear. All right, so that's the warm-up. What I want to do is to dig into what we're doing today. It really just pieces together some things that we've seen, and if you follow a certain habit, and in fact the habit is trying to be demonstrated through the warm-up, then you don't really have to worry about much. Now, sometimes people, I don't know if it's out of laziness. There's a lot of things that can go wrong. Yeah, it's probably not out of laziness, but perhaps the way to be lazy while being correct in the work is method 1, as we'll keep calling it today. So before digging into that, let's just say this much, right? To step back for a second and say you've got a definite integral. So if you're given a definite integral problem, you have an integral from provided x value called a, provided x value called b, function f of x, then let's say that for the specific problem you're given, you've decided not to find the number using area formulas. Maybe it's because it's not possible that way, like in the warm-up we were looking at. I should comment, though, in parentheses here, there are definite integral problems where the only method is to use area formula. So I'm thinking about when an absolute value shows up as part of your f of x, or if your f of x ends up being half of a circle. Okay, there are a handful of situations where you must use area formulas, but let's say you've decided to go about doing this without using area formulas, meaning you're going to use the fundamental theorem of calculus, meaning you need to find an antiderivative. So what you should do then is look at the indefinite integral, and here's what I want to emphasize, on its own line. So no equal sign is what I'm trying to get at, right? So you've got the original question is up there, and in starting your answer without an equal sign, you're just like, here's the indefinite integral, and then you find the antiderivative. Don't forget the plus c on that. The process of finding antiderivative might require substitution or might not require substitution. So it just depends on the integral problem you have. Some of them just require maybe FOILing first and then find an antiderivative of one term at a time. Other times you need to use substitution. So then once you've done that work, right? So this is I mean, this is sort of decision making. There's probably no writing in this process. Over here was the first bit of written work. It was working on the antiderivative. Once that's done with its plus c, then on a new line, again, I'm trying to say don't set equal this thing to the work from over here. So on a new line, use an antiderivative of f of x, and let's call it capital F of x to copy our notation from last Wednesday. It tends to usually be most convenient to pick for the plus c, which is required in the indefinite integral part, to pick this to be 0. And then you apply this fundamental theorem of calculus we saw last time. So the definite integral problem turns into the y value, or the output of capital F, of the chosen antiderivative at two different x values. The first x value you should use is this upper x value of b, and then the second x value is a. And I do want to recall that last Wednesday we had done this problem in that manner. So this is the first use of the fundamental theorem of calculus we had last time. This is going to be useful today, so I'd make sure to write this down if you don't have it written down from last time. Integral 4 to 10. 3x squared dx equals 936. If you recall, I showed you a picture of this, that it was really three sides were straight, one side was a curve that came from a parabola, and we found that the actual area here was 936 units exactly, which is kind of surprising to me that with that curve in place, there was really an exact area. So with this in mind, I would just kind of hold on to that off to the side. I'd like to look at this question. Integral 4 to 10 of quantity e to the power x over 3, then plus 8, close parentheses, square times e to the x over 3 power dx. We are going to try this question twice. I'm going to show you my preferred method first. So method 1, this looks just like how the warm-up went. Right? So if you're consistent about this process, then today's thing doesn't actually have to be all that strange. A lot of the pieces should feel very familiar. So step 1, just write the indefinite integral on its own line. I wrote indef here to try to remind myself not to put an equal sign accidentally here between this and that, right? So these are not equal. They're related. They're just not equal. Okay, one will help. Finishing this problem will help us with this problem up here. Okay, so I wrote down the indefinite integral. Integral quantity e to the x over 3 plus 8, close parentheses, squared, times e to the x over 3 dx. This will be done by u substitution. Let me mention right now that the u that is going to work here is u equals what was in parentheses. So e to the power x over 3. Then outside of the exponent, back in regular point font, it would be a plus 8. So then the derivative, well, you have to differentiate one term at a time. The 8 is nice to differentiate, right? This 8 constant will differentiate to 0. E to the x over 3 will differentiate to e to the x over 3 times the derivative of x over 3. Now, when taking the derivative of x over 3, I wouldn't use the quotient rule, though you can. It's much nicer to think of differentiating x over 3 by instead differentiating 1/3 x. And the derivative of 1/3 x is 1/3. So that's where this extra 1/3 comes from. It's from the chain rule. Okay, then if you work through, multiply both sides by dx and do a couple things here, I'll spare you some details right now. You end up with dx. When you solve for dx, you end up with the fraction 3 times du over e to the power x over 3. Now this x over 3 is a power. I know it's a little kind of small, but just want to clarify that. Okay, we've got a selection for u that will work. We have dx isolated, and now we can go back to the indefinite integral and substitute some pieces here. So I hope this looks okay. What was in parentheses is now just a u. That's what we selected for u. And then this e to the x over 3 was still copied. The dx right here was replaced with this fraction because that's what was right there. how we had solved for dx. I hope that step looks all right. The issue here is this integral still has a mix of x's and u's. But take a look. There's an e to the x over 3 in the denominator and 1 in the numerator. So those factors cancel out. And we're left with integral 3u squared du. Okay, we still haven't found an antiderivative at this point. That's why every time these steps you keep seeing the simple antiderivative of. Now, though, staring at this antiderivative of 3u squared, I think we're ready to state what that antiderivative is. We have u cubed plus c. Notice now there's no more du, there's no more integral sign. There is a plus c, however. And then one last thing to do to finish this indefinite integral problem is replace u with e to the x over 3, e to the power x over 3 plus 8. So sorry this spilled onto another line, but that's kind of how this work looks. So what we have done is, by doing a u substitution, we've completed this indefinite integral problem. Sorry for how this work spills, so what I've done to try to summarize it is the following. So I took this, and it is equal to eventually, now we have all this work. Right now the work is going to get in the way of what we want to say. So I highlighted this, highlighted that, those are equals, and I just put those right there on a line by itself. You wouldn't, on paper, on the final, you wouldn't be required to write a line like this on its own, but for the sake of looking at in-class slides, I think it's helpful to have this here. Right? So to summarize, we had this equals that. That's right here. This eventually equaled that. But now that we have the result of the indefinite integral problem right here, we can look at, this represents many possible antiderivatives just when you pick a different c. So I would like to just use this part for the next thing. Now we go back to the definite integral up here. So the definite integral, I copied the original question. So for a long time we weren't working with the original question. We were working with this related thing of the indefinite integral. But now take this definite integral, and I took this part right here and plugged in, and I even highlighted in red the x. I plugged in x's 10 first, and then plugged in x's 4 next into what's circled. And so that completes this. I want to pause for a moment and see if we're doing okay with that. Okay, I'd like to demonstrate a second way you can write up the work. I will go so far as to say this method is the thing that students always try to do, even though it's a lot more writing. So we'll go through it because people seem to want to do this. There's a temptation. So it's the same question. Sorry for the updated question number. Method 2, same choice of u, so the same dx as before. But to make this method work, you actually have to do this extra work of, here it's dx, so this x, when x is 4, how do we get what the u value is? Go back up here, right? So you plug in 4, and you have e to the 4/3 plus 8. That's what u is. And same deal, looking at the other x value of 10, you plug in x equals 10 into this to find out when x is 10, u is going to be e to the 10/3 plus 8. Then, so this method stays with the definite integral the whole time, but it is way more work in my opinion. So there's the question. We've done some work off to the side, but now we can take the original question, and here's what it's equal to. So a lot of the same substitutions are going on. The u that's right, so this part right there in parentheses was still u, so there's a u and then the square to account for that. There's still this e to the x over 3. The dx, as before, got replaced with this fraction. You'll notice something real funky that's different though. Right? The thing you'll notice is instead of just having a 10 and having a 4, there's this and that. Okay? And the reason is because right now, right away, from having replaced the dx, there's not a dx over here, there's a du. And when you see this du right over here, what needs to be in these spots where the integral is, those have to be u values, not x values. And you'll notice that u values, the u values are take up more writing. The x values were just 4 and 10. The u values are e to the 4 thirds plus 8, e to the 10 thirds plus 8. So continuing this problem and writing this again now in the next step. So we do have definite integral. By the way, we do have definite integral set equal to a definite integral. There's no error of indefinite integral set equal to definite integral or anything like that. But we can cancel here the e to the x over 3's. Still the endpoints of integration are these funky numbers, e to the 4 thirds plus 8 to u equals e to the 10 thirds plus 8 of 3u squared du, and then anti-differentiating, you'll have a u cubed. Now, since this should be a number, we had a definite integral here. We need to write in a format where we're gonna still don't set a definite integral equal to an indefinite integral. So I have this u cubed, which will evaluate at these two u values, and plugging in u is e to the 10 thirds plus 8 first, and then still the cube from right there, and then after the minus sign, plug in the other u value. So this ends up being the same. This right here, underlined right there, is the same final answer as we had before. To illustrate, I would just end here if you're going to use this method, but to illustrate a point, I put this into a calculator and got approximately 45,000. I think the most confusing step when doing it this way is the following right here. I try to point out in the first moment. So right away when you substitute dx, if you plug in for dx, you no longer have a dx, right? You plug in for dx and you have this other thing instead. And the moment that you have this du, since the highlighted this integral right here, since this has a du right there, the endpoints of integration must be u values, not x values. Okay, so because we need to have u values in these spots that are shown in red and that I just underlined, that is why we found out what u corresponds. We found out which u corresponds to x equals 4 and which u corresponds to x equals 10. That's what this extra work over here was about. I will point out a very common incorrect thing that people will do is they'll take this question right here and say that whether it's in this step or this step, it ends in du's. And what will happen is instead of having these numbers, which are correct up there, they'll just keep the 10 and 4. People just copy the numbers that appeared right there. What's shown in red right here is incorrect, right? It is incorrect to do this because this is a u right here, and this 10 and this 4, these are not u values, those are x values. And in fact, what happens when you imagine you write integral 4 to 10 3u squared du, just give that to somebody without showing them what we've done in class. What are they going to get when you give somebody the problem integral 4 to 10 3u squared du? They should end up getting 936. This is why last time, other than the fact that there were x's in these two spots, but the point is, without this problem, if you just give somebody integral 4 to 10 3u squared du, that's the same as giving somebody integral 4 to 10 3x squared dx. And if they followed the process we had last time, they'd go through and they'd get 936. But the point here is 936 is not 45,000. So you have to be careful if you're going to do this method. This method is the one that students always seem to gravitate towards, but it is more work. It's a lot more writing if you compare this version to the last version. I'll pause for a second, see if we're okay with this. Okay, I do have another example that I usually hand out on a sheet of paper, and I thought it would actually be helpful to go, so that's what's linked in the slides. I thought I'd go through this example because it's a smaller example, and sometimes it's not good to start with a smaller example, right? But here you've got this centered in the middle is this example integral 3 to 5, 2, 2x over 1 plus x squared quantity, then squared dx. So what I think method 1 or solution 1, which is preferred, is just start with the indefinite integral, right? Like, it's less work to indefinite integral, and you'll see here there's this u substitution that's made. You end up with this integral, integral 1 over u squared du, and that ends up in the end, the result of that indefinite integral is negative 1 over 1 plus x squared, then plus a c. So with this indefinite integral work, going back to the definite integral that's at the top, so it's written here, definite integral becomes, and I've taken this and I did the vertical bar notation if you'd like that, to plug in a 5 first and then a 3 next. And you end up, in the end, I think a good place to stop without a calculator is just negative 1 over 26 plus 1 over 10. That's a good place to stop. But to illustrate the same point as earlier, I went ahead and simplified this to be 4 over 65. This is usually the least amount of writing. If we go through that method 2 like thing, so I copied the problem that's up at the top that's centered that says example down here. You use the same u, right? So you'd still use 1 plus x squared, but you have this same conversion as earlier of you've got to convert when x is 3 from down here in the integral, then since u is 1 plus x squared, you plug in 3 of 1 plus 3 squared, you'll get u equals 10. In the same way, you'll get u equals 26 when you plug in x is 5. So here's what the updated definite integral looks like. Since this integral right here ends in a du, the endpoints of integration have to be u values and not x values. Right, so that's why this is an integral from 10 to 26, not an integral from 3 to 5. Integral from 3 to 5 is incorrect here, right? Integral from 10 to 26 of 1 over u squared du. And then at this this integral, you compute, and you actually never go back to x values here. Everything stays u's, but you do end up with the same final number here of 4 over 65. So this process works. Solution 2 does end up usually involving more writing. The incorrect thing that people tend to do, it looks like this. So down here where it says incorrect, starting with the definite integral, okay, u is 1 plus x squared again, and right away, the moment you substitute this dx, you have this du right here, and people will have this integral 3 to 5, 1 over u squared du. This will happen, and somewhere in the process, if you get lucky, you go back to substituting things back, and then these 3 and 5 refer to x's again, you would end up with 4 over 65. The problem is, and I've underlined these 3 down here, if you take any of these 3 problems and you just hand them off to somebody else without showing them the sheet, they won't get 4 over 65. You should work out that they will actually get 2 over 15. So the thing is, I think there's a lot of trouble that can come about when doing substitution and sticking with the definite integral the whole time, like this method 2 is shown here. I think the preferred thing is to just work on the indefinite integral. There ends up being less writing overall, less chance for error. As a way to correct this incorrect one, here's something that's acceptable, but it's more writing. All I did was I literally took this line over here that I'm highlighting, and in the 3 incorrect things, to just insist that they're not u values, because you would normally expect u values here, I will accept if you write x equals each time, here, there, and in the next one, right? So that's the way to correct these 3 things underlined here that are actually incorrect, is though u values are being expected, if you just write x equals to specify these are x values, that will work. But that ends up being more writing as well. So look, on this sheet, which you should download and have a copy of and take a look at, there are 3 completely correct solutions, solution 1, solution 2, and then acceptable but why down here. But there's this incorrect thing that people do. This incorrect thing is, I think it's an attempt to do this second solution, which is in any case still more writing than solution 1. I hope I can convince you from that much that it's just way more helpful to, I think it's just way easier, more convenient to write the indefinite integral. So we'll do that again in this problem. So I've got integral from 0 to 3, x e to the x squared plus 4 dx. So just write the indefinite integral on its own line. You don't have to worry about all this stuff. Indefinite integral on its own line. I'm going to pick a u. U will be x squared plus 4. So d over dx is 2x. Solving for dx, you'll have du over 2x equals dx. Okay, sticking with the indefinite integral, let's substitute some things here. So the exponent, which was an x squared plus 4, is replaced with a u. Dx is replaced with du over 2x. Aha, there's this cancellation of x here and there in the numerator denominator. That's good. Otherwise, we'd have this mix of x and u's. So having canceled that, we have integral 1/2 e to the u du. This is good, right? Now this integral, it doesn't have a mix of two different variables. It only has u's. Okay, so this is, I think, a nicer integral than the original indefinite integral. Okay, but we're down to one variable still, and it's a much nicer one variable integral than this one is. So now's the time to think about the antiderivative. Remember that e to the x is its own derivative, therefore e to the x is its own antiderivative. So we'll have here 1/2 e to the u plus c. We've antidifferentiated. It just so happens this function is its own antiderivative. And then we just need to replace the u. So we'll have 1/2 e to the x squared plus 4, then plus c. So then this is the correct work for the antiderivative problem with the plus c, but now we're going to focus on this, right? We're going to now focus on the 1/2 e to the x squared plus 4 and go back to the definite integral that's at the top. Right here. And then using just that part right there, plug in 3 for x and then plug in 0 for x. And I would just leave it like that. Right? For the sake of, just to kind of clean this up, this is fine as a final answer right there. But I went ahead and simplified the exponents to be 13 and 4 for this one. Okay, again, what I'm doing here is showing that method 1 because I think it's less writing. It leads to the fewest number of errors. But if you're going to try to do something like a method 2, here's what tends to happen, right? In the step, like right here, sticking with definite integrals the whole time, right at that moment when that substitution occurs and you have a du, this is 0 and 3, those are x values, not u values. So this is actually incorrect. So avoid that. And then just another version of it later, like the next step, same deal with 0s and 3s. Well, again, there's a u here. And the 0 and 3, those are not u values, those are x values. So if you gave either of these problems to somebody on a different day and they didn't see the original question up here, they're not going to get this as a final answer, given this question. Right? They're going to get something else. Okay, so again, to make the point, if a definite integral has a du instead of a dx, the endpoints of integration must be u values, not x values. So instead of this right here, which is incorrect, the correct way to write it would have been this: integral 4 to 13. I didn't go through all the steps of showing how that 0 and 3 translate to 4 and 13, but it involves this u is equal to x squared plus 4. Okay, so I'd like to ask you to work on these. Solutions are already posted if you wanted to look and click on the link. But I will give you a little time to work. And I will say, please form a habit right now of just using proper notation. Presenting this work matters. Of course, ask any questions or ask for a hint, anything like that you'd like to. Yeah, I can certainly talk through question two. So first, the indefinite integral, right? So no equal sign here, not yet, right? So I'm just, off to the side, indef, just to make sure I don't set it equal accidentally. Got the integral x over root x plus 2 dx. And we'll need to do a substitution, so maybe even more off to the side, maybe just up here. X plus 2, then du over dx will be 1, right? Because x differentiates to 1 while 2 differentiates to 0. Solving for dx, so du is equal to dx. Oh, yeah, okay, well, then we've already solved for dx. Normally you'd multiply both sides by dx and then do more. Here we'll have integral x over root u. The dx becomes du, as we see from over here. Oh, we still have this x left over. Well, okay, you remember u minus 2 is equal to x, subtracting 2 on both sides. So this integral becomes integral, x is replaced with u minus 2, so u minus 2 over root u du. Now we've seen this kind of algebra kind of a number of times, so we'll have integral. So u over root u should end up being a root u, in other words, u to the 1/2, minus 2 so the 2 over a root u, well, I'll write this as a u to the negative 1/2 power du. And then completing this antiderivative, so no more integral sign, so u to the 3/2 over 3/2 minus 2 times u to the, is that a 1? Yeah, I think that's, sorry, that was a poorly written, sorry, it's this pen, right? U to the positive 1/2 over 1/2, because the exponent used to be a negative 1/2 up there. And then a plus c, and then replace the u, where is it? Oh yeah, up there with x plus 2. So x plus 2 to the 3/2 over 3/2 minus 2 times x plus 2 to the 1/2 over 1/2 plus c. So there's the antiderivative. Now we can actually go back here, and now an equal sign is fine right here, staring at just this part. Now I did need to write the plus c over there. In fact, you see a plus c on 2 separate lines. But over here, now we can plug in the 7 for x first. So have 7 plus 2 to the 3/2 over 3/2 minus 2 times, now plug in this 2 next for x. Oh wait, so no wait, not yet. There's two terms here. I need to finish writing down plugging in 7. It's just a big thing that we got to plug into. Sorry about that. Over 1/2. Okay, so that was taking this underlined text over here and plugging in 7 for the x's first. And now we need to take that same hunk of text here and then plug in, sorry, this is now getting in the way. We need to plug in 2 for x next. So 2 plus 2 raised to the 3/2 over 3/2 minus 2 times 2 plus 2 raised to the 1/2 over 1/2. Sorry about that. Does that work? Sort of. The spacing was a little bad here. I didn't. If you click on the link, advancing one slide over, there's a link, and it is laid out way nicer. So, does that work? Or I'm curious where you got stuck. I'm guessing maybe it was, we've had to have this integral that has u's and x's both. Maybe that was the place. I'm not sure. I mean, you don't have to tell if you don't want either. But oh, okay, yeah, sure. And the algebra can look different, right? There's lots of other ways the algebra can look to still get to. For instance, a very common algebra way that some people don't like that 3/2 in the denominator, so would prefer to reciprocate and write like 2/3 u to the 3/2 minus, and then same deal, instead of this 1/2, multiply by 2 over 1. Oh, so 4 u to the 1/2 plus c. So, and then, right, so yeah, there's other ways this can look for sure. so I'll just do so please try, all four of these. And I know this fourth one looks a little strange, but it really does work out. And it's a good practice of the definitional logarithm, things like this will keep appearing. Um, for instance, in the last exam, so I'm 75% done grading. So I actually, uh, unlike last time where it took 5 hours to transfer the files, um, didn't have to do that. So only took 1 hour this time. You should be getting those back later today, in fact. Anyway, do click on that link for the key and go through and make sure everything looks okay to you. Let me just take a moment to just summarize where we are and say, let's see. So you have a definite integral. Um, the final answer to such a problem is always going to be a number. That number represents signed area. Now, one option is to interpret this as a signed area. And in fact, there's like certain problems where the function f of x here looks like this: root x squared minus, root 49 minus x squared. The only way to interpret that is as an area, to draw a half circle. The only way to do it, if you have your f of x has absolute value in it, is to draw that absolute value function, which looks like a v. In this case, you need to. I did not put all the details on this slide because I'm trying to do other things here. But this one, this v touches the x-axis right at x equals 5, and then the two v shapes have slope either plus 2 or minus 2. So that's one method. You can always try a problem using the method of signed area, but method 2 is to look at an indefinite integral. And when you do that indefinite integral, at the end, you've found an antiderivative. Don't forget to stick the plus c on there, and then apply the fundamental theorem of calculus. And then the comment here, and I've added to it compared to what we had last time. So there's pre-substitution rules. There's undoing the power rule, for instance. There's a couple rules that we learned before we ever talked about substitution. Sometimes instead of using one of these right away, you need to do some algebra first. Maybe it's taking care of this fraction or foiling out something, distributing, something like that. Finally, there is U substitution. And then the whole point of what we're looking at today, to be careful with notation, is you should be careful if writing definite integrals that involve substitution. I think the most helpful way to do this is to write an indefinite integral first, especially if you're doing substitution. I mean, just to do that anyway, it involves the fewest number of errors, and it allows you to have a uniform process all the time. In fact, if you click on the link that was on the previous slide, I wrote in red each time the most common errors, the most common incorrect things that people tend to write down. So please look for that. With that, this is the last week of classes, right? So the announcements are a little longer, so just kind of bear with me. I think if you listen through this once carefully, then I'll make the same careful announcement each day, but you'll have to listen through once, I guess. There's online quizzes Tuesday, Thursday this week. Please start WebWork 42 today. Again, it's easy to just start the one that's due today, but that will lead to frustrations. Monday, Tuesday, Wednesday, and Thursday, I have office hours as usual for this week. Friday, unfortunately, I have some meetings with the department and so on. I was going to offer office hours on Friday, but I don't think it's going to work out. What I am doing is having office hours in the morning and in the afternoon on Saturday, May 9th, Sunday, May 10th, Monday, May 11th. So these times are uniform. Or by appointment. So even on these days and that Friday, if I can figure out some timing, just if you want to meet and talk about some math prior, let's make that happen. The final exam for this class will be available on Tuesday, May 12th, and should be turned in by the end of the day on Wednesday, May 13th. Same kind of thing. It's now a 6-hour block because the final is officially 2-hour block of time. I don't write a final that's twice as long. So my final exam is not twice as long as an in-class exam. It's somewhat shorter than that. It's a little longer than an in-class exam, but so that I think the 6 hours is going to be fine in terms of timing. And if you run into some issues, of course, send me an email. I'm looking for a single PDF file. with all the questions answered in order and showing work. I think that is an issue that came up for a handful of folks with the exam that I'm almost done grading here. And just um, I've updated the final exam slide and made a copy of it right here. That I just why Tuesday? Well, originally our exam was scheduled to be at 7:45 a.m. on Tuesday, May 12th. So instead, what's going on is you'll have an exam available to you starting on Tuesday, May 12th, needing to be turned in by the end of the day on Wednesday, May 13th. But just like with exam 3 and exam 4, so in this 48-hour block of time, you need to choose a 6-hour window of time in which to work on the exam. I don't think the exam should take anybody longer than 2 hours. If I mean, really an hour and a half. If you want to use 2 hours, if you want to use 3 hours, fine. But that's not the exam is not meant to take a long, long time. Um, Again, turn in one file, and I will be posting practice materials in Canvas for this. Actually, one final comment here. Please keep current with WebWork. The final WebWork assignment, I had to remove some assignments because of how things went. Of course, losing a week of class. But the final assignment, 44, if you follow the dates that I'm suggesting, should be started on May 6th. That's this Wednesday. But because of when they're finally due, during final exam during the first part of final exam week, I made the last two assignments extra credit. All right. I will stop the recording.